Hello all, welcome again. Please subscribe to our channel if you did not subscribe to our channel by clicking subscribe button and the bell icon for your personal notifications. In the series of STM32H7 tutorials, today's the topic is power control. In this we'll look into the power management and supply overview, power schemes, supply configurations, step-down converter, LDO regulator, backup main domain regulator, other regulators like USB DSA regulator and voltage supply supervision, POR or PDR and BOR, power on reset and all, and temperature supervision, battery charging, system definition, power management, and voltage scaling modes, run modes, CPU operating modes, domain operating modes, system operating modes, system power control states, sleep mode, stop mode comparison, standby mode, VBAT mode, and CPU entering CSTOP mode, CPU wakes up from CSTOP mode, and software low power procedure. Whereas wake up, power interrupts, option bytes, debug information, and the related peripherals will be discussed in this. So STM32H7 has several key features related to power management, including several low power modes where it is still possible to wake up the MCU with an event on an IO, as well as large number of peripherals that can wake up from the various low power modes. The D3 autonomous mode allows transfer of data on communication peripherals without waking up the CPUs. Several power supplies are independent, allowing reduction of the MCU power consumption, while some peripherals are supplied at higher voltages. Thanks to the large number of power modes and independent power domains, STM32H7 devices offer high flexibility to minimize the power consumption and adjust it depending on active peripherals, required performance, and needed wake-up sources. The integrated step-down converter reduces STM32H7 power consumption at minimal cost. STM32H7 device have several independent low power supplies which can be set at different voltages or tied together. The main power supply is VDD, supplying almost all IO except for some IO of port A, C, and B. VDD also supplies the reset block, temperature sensor, and all internal clock sources. You can see in this power scheme. In addition, it supplies the standby circuitry, which includes the wake up logic and independent watchdog. VDD supplies the step-down converter, which may directly provide the vCore supply. vCore supplies the three domains: CPU1 Cortex M7, CPU2 Cortex M4, and D3 domain, with most of the digital peripherals and the SRAMs. The flash memory is supplied by both vCore and VDD. vCore may be supplied through the voltage regulator, which is supplied on VDD LDO. The STM32H7 features several independent supplies for peripherals: VDDA for the analog peripherals, VDD 50 USB, and VDD 33 USB for the USB transceiver, VDD DSI and VDD 1 to DSI, that is 12 DSI for the DSI physical layer. The V reference plus pin provides the reference voltage to the analog to digital and digital to analog converters and can be used as an external buffer reference for the application. A backup battery can be connected to the VBAT pin to supply the backup domain. So you can see all those in green or USB and black or VDD-SI, VDD. So various color representations have been given here. The main power supply VDD ensures full features operations in all modes, power modes from 1.71 to 3.6 volts. So the analog power when device functionality is guaranteed down to 1.62 volts. The minimum voltage after which a brownout reset BOR is generated. Other independent supplies are provided for peripherals operating at different voltage. The analog voltage power supply VDDA can be connected to any voltage other than VDD. When the analog to digital converters or comparators are used, the VDDA voltage must be greater than 1.62 volts. You can see here 1.62 volts. When the digital to analog converters or comparators are used, the VDDA must be greater than 1.8 volts. When operational amplifier are used, VDD must be greater than 2.0 volts. The USB regulator supplied from VDD 50 USB at 5 volt generates the USB power supply VDD 33 USB. When the USB used VDD 33 USB must be greater than 3 volts. The DSA regulator supplied from VDDSA greater than 1.62 volt generates the DSA power supply VDD 12 DSA when the DSA is used. The VDD 12 DSA must be greater than 1.2 volts. A backup main domain is supplied by VBAT, which must be greater than 1.2 volts. The backup domain contains the RTC, the 32.768 kHz LSC external oscillator and 128 byte backup registers. The ADC and DSC voltage reference can be provided either by external supply voltage or by internal reference buffer. This allows the converter's performance to be improved by providing an isolated and independent reference voltage. Let's quickly jump onto the supply configuration, that is SMPS, step down converter, SD converter can be used in 3 differential modes as shown here. 1. Direct supply, the V-core domain as shown in figure configuration 2. This offers the lowest power consumption. 2. Used to supply the voltage regulator at an intermediate supply level as shown in configuration. 3. This offers low power consumption with a low noise V-core supply. So used to supply external circuitry as shown in configurations 4 and 5. In this case, the voltage regulator can still be supplied from the same external supply provided by the step-down converter. 4th is disabled as shown in configurations 1 and 6 here. This offers a low-cost solution at higher power consumption rates. The STM32H7 startup, the supply configuration is programmed in PWR controllers CR3 registers. This register is write once to protect against accidental overrides. The step-down converter cannot be used to supply the STM32H7's VDD supply, but can be used to supply the VDD IO2 supply. Let's quickly jump onto the step-down converter. When directly supplying the V-core domain, the step-down converter provides the supply voltage according to VOS and SVOS scaling. The step-down converter's operating mode follows the device mode. When used to supply the voltage regulator, the step-down converter may provide an intermediate voltage at 1.8 or 2.5 volt. The step-down converter's operating mode follows the device mode. The step-down converter is used to supply external circuitry. It may provide a voltage at 1.8 or 2.5 volt. In this case, the operating modes are fixed to high performance. So there are 3 operating modes, right? High performance, low power and standby. So when used, the voltage regulator provides LDO regulator is there. When used, the voltage regulator provides the V core power supply according to VOS and SVOS scaling. The voltage regulator operating mode follows the device mode when the V core is supplied from another supply. So backup domain regulator, backup is used to keep the context of the backup RAM in standby and VBAT modes. The backup regulator is enabled by BREN bit in PWR register CR2, power register CR2, and checks its readiness before entering standby or VBAT mode. So other regulators are USB regulator and DSI regulator. An independent USB regulator generates VDD33 USB from 5V supply. Let's have some thing onto the supervision, power supply supervision. So power supply supervisor ensures dynamic power supply management. STM32H7 devices embed power management on main VDD, analog VDD VBAT supply input, V core domain, backup VSW domain, backup regulator VBKP supply, step down converter, VFBS MPS, VFB SMPS. Okay, USB interface, VDD33 USB supply, and DSI, VCAP DSI supplies. The main VDD supervisor handles reset management and voltage detection via the programmable voltage detector PVD. When VDD crosses the selected threshold, the PVD can be enabled in all modes except standby modes. 7 thresholds can be selected by software. In addition, comparisons can be done with an external pin. The analog VDDA supervisor handles voltage detection via the analog voltage detector AVD, and VDDA crosses the selected threshold. The AVD can be enabled in all modes except standby modes. 4 thresholds can be selected by software. The VBAT supply voltage is monitored to detect when VBAT crosses the minimum and maximum thresholds. The VBAT voltage detection function can be enabled in all modes. The main V core power supervisor handles reset management and over voltage detection. The backup domain VSW supervisor handles reset management when the supply drops below the operating level. The backup regulator VBKP supply supervisor verifies that the regulator is ready to supply the backup RAM before entering standby mode. The step down converter VFB SMPS supply supervisor verifies that the converter ready and supply is at the selected level. The USB interface VDD33 USB supply supervisors verifies that the USB interface supply is present. The USB supervision can be enabled in all modes except standby modes. The DSI regulator VCAP DSI supply supervisor verifies that the DSI regulator is ready to supply the DSI interface. So VDD power supply supervisor guarantees a safe and ultra low power reset management. STM32H7 devices embed an ultra low power brownout reset BOR, which is always enabled in all power modes. The BOR ensures reset generation as soon as the MCU drops below the selected threshold, regardless of the VDD slope. 4 thresholds from 1.62 to 2.78 volt are selected by option byte programmed in flash memory. The BOR consumption with the 1.7 volt threshold is indicated in the data sheet. We have one more supervision called as temperature supervision. The temperature supervisor detects when the junction crosses the minimum and maximum threshold. The temperature detection function can be enabled in all modes. Now let's move on to the battery charging. The battery charging feature can charge a super cap connected to the VBAT pin through an internal resistor when the VDD supply is present. You can see in this figure. The charging is enabled by software and is done either through a 5k ohm or 1.5k ohm resistor depending on software. Battery charging is automatically disabled in VBAT mode. And system definition, let's quickly move on to system definition. By allocating peripherals to a CPU or the D3 autonomous mode, the boundary of the subsystem can be controlled. The subsystem will follow its associated CPU or D3 autonomous mode operating mode. This is used to optimize the subsystem's power consumption. Peripheral allocation is done in RCC via the PER XEN and PER XAMEN register bits, enabling the automatic wake up of the domains associated with the woke-up and subsystem. Let's see at a let's look at a block diagram of a system definition much further. When CPU1 is in C-run mode, the fixed allocated D1 bus matrix and D3 bus matrix peripherals are clocked. Other peripherals may be allocated when needed. You can see in this figure. When allocating a peripheral in D2 domain, the D2 domain will be powered and D2 bus matrix with its fixed peripherals and the CPU1 allocated peripherals will be clocked. When CPU2 is in C-run mode, the fixed allocated D2 bus matrix and D3 bus matrix peripherals are clocked. Other peripherals may be allocated when needed. When allocating a peripheral in the D1 domain, the D1 domain will be powered and the D1 bus matrix with its fixed peripherals and the CPU2 allocated peripherals will be clocked. When D3 is in autonomous run mode, the fixed allocated D3 bus matrix and the D3 domain autonomous mode allocated are clocked. So this raises a question. We should have a power management for domain partitioning D1, D2, D3, isn't it? So power management functions controls the power supply for different domains. Yeah, excuse me. So power management function controls the power supply for the different domains based on the domain operating mode. The system and domain operating mode depends on the CPU operating mode and the CPU's subsystem boundaries. You can see the operating mode, CPU modes, C-run, C-sleep and C-stop, domain modes, D-run, D-stop and D-standby. System modes are run, stop and standby. So voltage scaling, run mode will have voltage scaling, provides 3 ranges by VBOS and similarly stop mode by SVOS, the same 3 ranges. So let's look into the voltage scaling in the coming to be followed after this. Thanks to the voltage scaling, the various run modes of the flexibility between the required performance and consumption in run mode, range 0, enhanced performance with high power consumption. The system clock is limited to 480 MHz. In run mode, range 1, that is high performance with high performance consumption, high power consumption, the system clock is limited to 400 MHz. You can see in this table. In run mode range 2, the medium performance and power consumption, the system clock is limited to 300 MHz. In run mode range 3, low performance, range 3 means low performance with the low power consumption. The system clock is limited to 200 MHz. The internal and external oscillators as well as the PLL can be used in all modes respecting the maximum frequencies. The run mode range is determined by the system clock frequency even when a CPU is CSTOP mode. In stop mode range 3, the peripherals with wake up from stop mode capabilities UART, SPI I2C and low power timer LPTIM are operational. In stop mode, ranges 4 and 5, the peripherals with wake up from stop mode capabilities are disabled. So each peripheral can be configured to be on or off in run and low power run modes. By default, all peripheral clocks are off except the flash interface. The SRAM clocks are enabled in run mode. When running from D1 SRAM, D2 SRAM or D3 SRAM, the flash memory can be put in power down mode thanks to the software, and the flash clock can be switched off. The flash memory must be accessed when it is used, when it is switched off. Consequently, interrupts must be mapped in SRAM using the Cortex M vector table offset register. The CPU entering low power mode is controlled by Cortex M, WFI and WFE, and deep sleep bit allows to select between C sleep and C stop mode. We will see that in the table. When the CPU enters the stop mode, the domain and system operating mode depend on the other CPU and the D3 autonomous modes. A CPU NVIC interrupt with sufficient priority will wake up the CPU after a WFI or return from ISR. A CPU event input will wake up the CPU after a WFE, that is RxEV. Okay. In addition, when the Cortex M SV on pend SVON PEND bit is clear, an NVIC interrupt with sufficient priority will wake up the CPU after a WFE. When the SV on pend bit is set, any NVIC interrupt will wake up the CPU after a WFE. So power management function controls the power supply for different domains based on CPU operating mode and domain. So we just saw C run, right? So we can talk about domain run, that is domain operating modes, like namely D run, power down deep sleep selection through PWR register with PDDS, DN. Each CPU has its own control bits for the three domains. A domain will only enter D stop mode when the domain CPU is in C stop mode and the other peripherals has no allocated peripherals or also in C stop mode. This is about system operating mode, domain operating mode. We quickly move on to the system operating mode, which is controlled from both CPUs and D3 autonomous mode. The CPU system will only enter stop or standby mode when both CPUs are in C stop mode and there is no active wake up source, or if the D3 domain is forced in run mode. The system will only enter standby mode when the power down deep sleep selection in power register bits PDDS_DN allows all domains to enter standby mode. The D3 autonomous mode can set the system in run mode either by a CPU forcing the D3 domain in run mode via its run_D3B register bit or by a peripheral backup source request. So system power control states are also available. The coming figure will give you the complete overview of power modes in relation to the CPU operating modes and the D3 autonomous mode. Here it is. The system power state is controlled by both CPUs and D3. So state transition may be initialized. If you want, I will expand it to you. So a CPU going to low power mode, a CPU, a peripheral allocation, deallocation, domain mode, a wake up event, change PDDS setting to a standby, that is domain mode, depicted in this. So let's talk about sleep mode first. Sleep and low power sleep modes enable all peripherals to be used and features the fastest wake up time. In these modes, the CPU is stopped and each peripheral clock can be configured by software to be gated on or off during the sleep and low power sleep mode. These modes are entered by executing instruction wait for interrupt or wait for event, WFE or WFI. When executed in low power run mode, the device enters low power sleep mode. Depending on the sleep on exit bit configuration in the Cortex M4 system control register, the MCU enters sleep mode as soon as the instruction is executed or as soon as it exits the low power lowest priority interrupt subroutine. I repeat, depending on the sleep on exit bit configuration in the Cortex M4 system control registers, this MCU enters sleep mode as soon as the instruction is executed or as soon as it exits the low priority interrupt subroutine. This last configuration saves time and consumption by removing the need to pop and push stack. This is about sleep mode. Let's move on to the stop mode. STM32H7 devices features 3 stop modes: stop range 3, range 4 and range 5, which are the low power modes with full retention and fast wake up time to run mode at 64 MHz. The contents of SRAM and all peripheral registers are preserved in all stop modes. All high-speed clocks are stopped. That 32.768 kHz external oscillator and 32 kHz internal oscillator can be enabled. Several peripherals can be active and wake up from stop mode. System clock on wake up can be internal high speed and low power, that is CSI oscillator up to 64 MHz with only a 12 microseconds from flash. Stop range 4 and range 5 consumption is lower than the stop range 3 but supports less active wake up modes. So in stop mode we can also have a stop mode hold to be able to reinitialize the clock system by so-called master CPU when exiting from stop modes. The stop hold function holds the so-called slave CPU until the master CPU has reinitialized the system. To do this, a slave CPU wake up from the stop mode interrupt will hold the slave CPU and wake up the master CPU with a wake up hold interrupt. That means once the master CPU has reinitialized the system, it clears the slave CPU hold, where afterwards the slave CPU will receive the initial wake up interrupt. Let's see a small comparison when with the stop modes, okay, of range 3, range 4 and range 5. When comparing stop modes, stop range 3 consumption is higher than stop range 4 and 5, but the wake up time is shorter and number of active peripherals is higher. Stop range 3 keeps the vCore domain at the same supply level as run range 3, allowing a very short wake up time lower than 12 microseconds when operating from the RAM to the expense of higher consumption than stop mode with the ranges 4 and 5. It is possible to wake up from stop range 3 with peripherals supporting wake up from stop mode: UART, SPI, I2C and low power timer LPTIM. There is another mode. Let's move on to the standby mode. Standby mode is the lowest power mode in which 4 KB of backup RAM can be retained. The automatic switch from VDD to VBAT is supported and IOS levels can be configured by independent pull-up and pull-down circuitry. By default, the voltage regulators are in power down mode and the SRAMs and the peripherals registers are lost. The 128 byte backup registers are always retained. Thanks to software, it is possible to retain 4 KB of backup RAM. The ultra low power BOR is always on to ensure a safe reset regardless of VDD slope. Each IO can be configured with or without pull up or pull down, which is applied and released thanks to the APC control bit. This allows control of the input state of external components even during standby mode. 6 wake-up pins are available to wake up the device from standby mode. The polarity of each of the 6 wake-up pins is configurable. The wake-up clock is HSI with a frequency of 64 kHz. In case if I am discussing any project here, I'll show you how to do it in Cube IDE and all those stuff. Let's move on to the VBAT mode. The backup domain allows us to keep the RTC functional and to preserve the backup register in case the VDD supply is down, thanks to a backup battery connected to the VBAT pin. The backup domain contains the RTC clock by the low speed external oscillator at 32.768 kHz. 3 tamper pins are functional in VBAT mode and will erase the 128 byte backup registers also included in the VBAT domain in case of intrusion detection. The backup domain also contains the RTC clock control logic in case VDD drops below a certain threshold. In case VDD drops below a certain threshold, the backup domain power supply automatically switches to the VBAT. When VDD is back to normal, the backup domain power supply automatically switches back to VDD. The VBAT voltage is internally connected to an ADC input channel in order to monitor the backup battery level. When VDD is present, the battery connected to the VBAT can be charged from the VDD supply. How about CPU entering the CSTOP mode? A CPU will enter CSTOP mode when executing an WFI or WFE with the deep sleep bit set. The domain and system state will also depend on the other CPU's operating mode and wake-up source status. Only when the other CPU has no allocated peripherals in the domain or the other CPU is also in the CSTOP mode, the domain may enter dstop or dstandby mode. I repeat, only when the other CPU has no allocated peripherals in domain or the other CPU is also in CSTOP mode, the domain may enter dstop or dstandby mode. When in addition none of the wake-up sources is active, the system may enter stop or standby modes. So entering from CSTOP mode, entering the CSTOP mode. How about wake up? CPU wakes up from CSTOP mode. It has to know from which mode the domain and the system have woken up. For this, CPU has dedicated flag bits SBF_D1, SBF_D2, SBF and stop F. These bits inform the CPU about the state of the system and which parts may be needed to be reinitialized. Have a look at this. Then we will move on to the software low power procedure. The Cortex-M sleep deep bit allows selection of CPU to enter C-sleep or C-stop modes. When the CPU enters C-stop mode, the power control PWR control bits PDDS_D1_D2 and _D3 respectively select which state the domains may enter in. The state of the domains depend also on the other CPU's subsystem configuration and operating modes and the wake-up source status. From C-sleep mode, the CPU will always wake up through an interrupt or event. In this case, the Cortex-M deep sleep bit is 0. Have a look at this. This is how it is. And from CSTOP mode, the CPU may wake up through an interrupt via reset depending on the domain state. If the domain state was in dstop mode, okay, the CPU woke up through an interrupt. In this case, the Cortex M deep sleep bit is 1. When in addition the stop F bit is 0, the system remained in run mode. So there is no need to initialize the clock system. If stop F bit is also set, it means that the system woke up from, sorry, that means it means that system woke up from stop mode and the clock system needs reinitialization. If the CPU has allocated peripherals in the other domain, check the other domain's SBF_DN flag, that may be 1, 2 or something, to know if the domain was in D standby mode. In this case, the peripheral in the other domain needs to be reinitialized. If the domain was in D standby mode, the CPU will wake up through a reset. If the SBF flag is also set, the system was in standby. In this case, a full system initialization is needed when the SBF flag is 0 and the CPU domain SBF_DN flag is set. The system remained either in run or stop mode, and only by the CPU domain has exited from D standby. In this case, only the CPU and its domain need to be reinitialized. Afterwards, the system state must be checked to know if the system remained in run mode or was in stop mode when the CPU domain SBF_DN flag does not indicate D standby. The CPU woke up via system pure reset. Okay. And after this, we'll have a quick glance at wake up. Anyways, if it is not clear here, please ping me. I'll provide you this via mail or something. Let's have a look at wake up and then power interrupts and option bytes available. So this table gives a complete overview of CPU domain and system mode and the wake up flag bits. It also shows how the CPU was awakened through an interrupt or an event or a CPU reset. Next, we'll see a summary of power control related interrupts. Okay, have a look at it. Description was given and availability. Then we'll talk about option bytes available. So 2 bits are available in option in the flash option bytes or prohibit entering a given low power mode. When cleared, these option bits trigger a reset when entering either standby or stop modes. This is a security feature used to reduce the impact of unintentional entry into these low power modes. If these low power modes are not used in user code, the option should be enabled. After this, we'll talk about debug control register, which is used to enable debugging in standby mode. When the related bit is set, the regulator is kept on and domains are supplied in standby modes. This maintains the connection with the debugger during the low power modes and continues debugging after wake up. Remember to clear these bits when the MCU is not under debug because the consumption is higher in all low power modes. When these bits are set, due to the fact they force the regulators to remain enabled. Okay, debug MCU underscore CR and underscore standby. You can refer to peripherals like reset, clock control, RCC, NVIC, XT1, DAC, comparator, COMP, low power timer, LP timer, independent watchdog, and RTC, I2C interface, UART or USART, LP UART, that is low power universal asynchronous receive transmitter, single wire protocol master interface, SWP, MI, OTG underscore FX, that is on the go full speed. For much. Thank you for your time. Please revisit if you don't understand it twice or thrice, so that you will. I know it's little confusing the way presented, but if you watch this 2 to 3 times, you will have much better understanding. Thanks for your time. Please subscribe to our channel by clicking subscribe button and press bell icon for your personal notifications. Please, if you like this presentation or video, please kindly share. Thank you, and press like button.